specific stuff from the homework. Again, the mass, volume stuff is really important. I think your book does a good job of it. I just want to walk you through a couple of examples that are a little more intense. First, I want to talk about writing the total ionic equation. This example is the example that it talks about in your homework, and I thought we could talk about it here so you didn't have to spend time reviewing it when you're in your homework. So we've been talking about ions, solubility, dissociation, dissolving. We're all familiar with the concept of something dissolving, and that's exactly what happens when you put it in solution. It dissolves. So just because I have potassium carbonate here does not mean it's going to exist always as potassium carbonate. When I put it in that aqueous solution, I'm actually going to get 2 potassium ions in aqueous solution plus a carbonate. So let me take a side note here. I know what the charge is on this carbonate ion because forever and always, table 6.7 is going to be helpful. It tells me my polyatomic ions, and there's my carbonate, and it tells me what the charge is on it. Okay, I've told you guys about this one before. You're going to continue to need it. And that's something I really like about chapter 9. It covers some stuff that we've already been over. It looks at it in a little bit new way, but in some ways it should feel like a refresher. And I hope that, feels like you have a little bit of breathing room because you'll know a few things. Okay, back to this. Hydrogen and bromine are also going to dissociate. And while we're talking about the text, let me also call out for you table 9.7, which is going to tell you which ones dissociate and which ones might stay together. Okay, so bromine dissociates except when combined with, okay, well, it's not combined with those, so I know hydrogen and bromine are going to come apart. Okay. Are we good? Is that fuzzy? I hope that's not fuzzy. It looks fuzzy. There. Okay, 2 H pluses in aqueous solution, 2 Br minuses in aqueous solution, 2 of them. And then on this side, okay, just because potassium and bromine are going to come together doesn't mean they're going to form that bond in solution. So I'm going to have those 2 potassiums hanging out exactly the same way on this side. I'm going to have to skip down here. The bromines also. But the difference is you're going to actually get CO2 gas. So 2 carbonates are going to lose an oxygen. You'll make 2 CO2s, and then each of those extra oxygens are going to come over and grab an H, and you'll get water. Excuse me. 1 oxygen, 2 hydrogens to make a water. Wow. Okay, so there's my total ionic equation. Again, this is the example. I just don't want you to have to review it when you're into your homework. It's going to be asking you to write some of the species of the reactants. And you need to be careful of your superscripts and whether it's an aqueous solution, a gas, or liquid. Okay, let's do a couple more math problems. Again, this should help you with your homework. What volume of silver nitrate is needed to completely react with 1 liter of 0.5 molar, with enough salt, sodium chloride, to give you 1 liter of 0.5 molar sodium nitrate? Okay, I have 2 molar, and molar just is a concentration, moles per liter. So that's my concentration, silver nitrate. How much of it do I need if I have an abundance of salt to get me over here and end up with 1 liter of 0.5 molar sodium nitrate? Okay, well, let's start with what I know. I know that I have 0.5 moles per liter of sodium nitrate, NaNO3, right? And I have 1 liter of it. So canceling that, I am in moles of NaNO3. And is this a balanced equation? Let's just double check. Silver, silver, yes. 1 chloride, yes. 1 nitrate, 1 sodium, 1 sodium. Great. That makes my stoichiometric ratio, or my mole to mole ratio, very easy. I can go from 1 mole of NaNO3 for every 1 mole of these. My stoichiometric coefficient is 1. I have 1 mole of these. My stoichiometric coefficient is 1. Okay, I have 1 mole of silver nitrate. Now I'm in moles of silver nitrate. And what else do I know about it? Well, I know its concentration. So if I divide by 2 moles per liter of it, then I'm in, see, I have to cancel my moles of sodium nitrate and my moles of silver nitrate, and I'm in liters of silver nitrate, which is exactly what I want, right? I want the volume. So this is just 0.5 times 1 divided by 1 times 1 divided by 2 breaks down to nothing but 0.5 divided by 2, which, if my math is right, is 0.25. 0.5 divided by 2 is equal to 0.25 liters of sodium nitrate. Okay, let's just say that I have 20 grams of silver chloride that came out of that reaction. Let me set this up right for you guys. Give me a sec. If I have 20 grams that came out of this reaction, and I know that I used 1/2 liter of sodium chloride to get it, what is my concentration or molarity of my sodium chloride solution? Start with what you know. I know I have 20 grams of silver chloride. 20 grams silver chloride. And I want to get to moles so I can get over to the moles of the other species. So 20 grams of silver chloride is, I'm looking at my periodic chart, it's 107.9, 107.9 plus chloride 35.45, 35.45. 143.35 grams per mole. And I'm going to put the grams on the bottom so it'll cancel. And then for every 1 mole of silver chloride, I have, for every 1 mole of silver chloride, I have 1 mole of sodium chloride. Okay, a 1-to-1 mole relationship, which again makes this very easy. 1 mole. And again, I know the volume of it. Well, let's go ahead and separate. Let's put this in. 20 divided by 143.35 is 0.14 moles of NaCl.